In the last example, I want to show how we can draw the output waveform at the load. Okay, until now we have done the calculation of the voltage gain, but so far we haven't done any drawing of the output signal, provided that the information on the input signal is given. So for this example, I will show you how we can draw the output waveform. Okay, so when you draw the output waveform, the important things that you need to consider is the point of the waveform. Okay, the point of the waveform. So usually we will draw the output waveform is at the load. So this is output waveform is at the load, which it is after the coupling capacitor. So this is your coupling capacitor. Okay, after the coupling capacitor. So the coupling capacitor will allow the AC signal, and then it will block the DC signal. Okay, so the signal, the waveform at the load will be the AC's, only the AC signal without the DC value. So what I mean by DC value is if there is no input signal connected at the input point of the amplifier, so this voltage at the drain, I put it VD, there is the value of the VD. So the VD here is a DC voltage. So how we can calculate the VD? The VD is equal to this VDD. For example, this one 13.6 minus voltage drop at the RD. So this is ID RD. Okay, for this example, we are consider the IDQ is 2.25 milli. 2.25 milli and RD is 3K. Okay, so this will give you the DC voltage at the drain point is 6.85. Okay, so this is the DC voltage at this drain point. So without any application of the AC signal at the input, so this point this voltage at this point is equal to 6.85. So once we add the AC signal at the input, so this value of VD will oscillate, will change depending on the AC signal. Okay, up and down, depend on the shape of the input signal. Okay. Okay, so for this question, want to draw the waveform at drain terminal. So we want to, this is the VD, the waveform at the VD, and at the load. So this is the V out. So this is the VD and this is the V out. Okay, the difference is, what is different between waveform at the drain terminal and at the load? So the waveform at the drain terminal is before the coupling capacitor. So before the coupling capacitor, you will have the DC signal plus AC signal. So you have the combination of the AC plus DC. But after the coupling capacitor will block the DC signal. So what appear across the RL will only the AC signal. Okay, so please remember this. The coupling capacitor block the DC signal. So at the drain point, the waveform will be consist of the AC plus DC. But after the coupling will block the DC, and the remaining signal will be purely a AC signal. This is the ideally the expected result after the coupling capacitor. Okay, so we want to waveform at the drain terminal VD and at the load Vout. When the V signal, we have the two condition. V signal is sine wave with the different V peak. Okay, and it is given that the gain Vout over Vin is minus 4.5. Okay, let's consider the first V signal condition. So the V signal is the sine wave with the V peak of 1. So this is 1 sine omega t. So the frequency, information on the frequency is not given. So we can ignore that. Okay. So the V signal, there is no internal internal resistance of the signal. So the V signal will equal to Vi. So this is equal to Vi. So we know that the AV Vout over Vi is equal to minus 4.5. So Vout is equal to minus 4.5 times Vin. So Vin is sine omega t. So we got the Vout is equal to minus 4.5 sine omega t. So this is the equation for the Vout waveform. Okay, so at the Vout waveform. But when we want to draw the waveform at the drain, so this is the Vd, and then this is the time. This is the 0. Okay, we know that the initial point for the Vd is the Q point. The Vd at the Q point. So this is, we have calculated as the 6.85. Okay, so this is the initial point. This is the 6.85. Okay, so when we add the AC signal, so this Vd will oscillate with the magnitude, the changes of magnitude. The peak voltage is 4.5. So 4.5 volt. So it will change from 6.85 to 6.85 plus 4.5. So this is 11.35, and then it will oscillate 6.85 minus 4.5. So this is 2.35. Okay. So the waveform will looks like this. Okay. So the sine wave is inverted because the gain is minus. So inverted because the gain is minus. So we have here, you see the Vd versus the time. We have the AC signal and we have the DC component, is what we call it a DC shift, or we call it, this is a shift. All the waveform AC signal is shifting upward. So this is the shift. The shift is a DC signal. So 6.5. So in terms of the equation, mathematical equation, the Vd is equal to the combination between the AC and the DC. So Vd is equal to minus 4.5 sine omega t plus 6.85. So this is the mathematical expression of the VD. Okay, so how the waveform looks like at the load. So this is V out over times. So at the load, this 6.5 will be filtered out. It will the DC shift. There is no DC shift. The DC component will be disappear. So what remain is only the AC signal. So at the output, we'll have the AC signal without the DC shift. So this is 4.5. This is minus 4.5. Okay. So again, the left hand side is the drain. This is the drain voltage versus the time. The right hand side is output voltage versus the time. So the difference is the waveform at the drain will have the DC component, but the waveform at the load will not have the DC component. Okay, this is the first condition. The second condition is when the V signal is a sine wave with the peak voltage of 1.6. So this is V signal equal to V in equal to 1.6 sine omega t. Okay. Based on the gain equation, V out over V in equal to minus 4.5. So V out is equal to minus 4.5 times 1.6 sine omega t. This is equal to minus 0.72 sine omega t. So the output will have the amplitude of peak voltage of 7.2 volt. Okay. So we again we draw the waveform. Let's draw the waveform at the drain first. This is the VD. Say this is the time. Okay. The initial point or the Q point or at the VD is 6.85. Okay, 6.85. Okay, so the after we apply the AC signal at the input, so this voltage point at the drain point will oscillate up and down. So the maximum value is 6.85 plus 7.2. So this is 6.85 plus 7.2 is equal to 14.05. So this is 14.05. Okay, and then the oscillation, the minimum value is 6.85 minus 7.2. So it will give you, okay, actually the scale is not that good. So let me redraw this graph. Okay. So this is the T, this is 0. Okay. The minimum value of the oscillation is 6.85 minus 7.2. So they will give you the negative value, which is minus 0.35. Okay. If you draw the waveform, you can draw something like this. but the actual waveform will not be like this, because the drain voltage is limited by the applied DC source. Okay, if you see the circuit here, the DC source is come from this 13.6 volt, and then it is grounded, so the possible value for the drain voltage will be, the minimum is 0 volt, the maximum is 13.6. So the value of VD should be within this value. So VD should be from the 0 volt until 13.6 volt. So this is the 13.6 volt and the value. So what will happen is, in actual graph, there will be a clipping. There will be a clipping. Okay, if I can okay, so there will be the graph will be something like this. Okay, so you will not have the clear or a clean sine wave, so you will give something like this. Okay, this is at the drain. So what happened at the load? So at the load, the DC shift 6.85 is removed, so we will get the waveform will become something like this. This is the V out over time. So this is the 6.85. Okay, the total the V peak is 7.2. So we have the we need to minus with 0.35. So this is the minimum is minus 6.85. Okay, minus 6.85. And then at this point, the clipping is until the 6.75. Okay, so this is the answer for the last example. Okay, the important takeaway point is, you need to understand the function of coupling capacitor. Okay, and then you see the waveform, the difference. You need to know the difference between the waveform at RL and at the drain. So at the drain is before the coupling capacitor. Okay, and then the third point is analyze or consider the possibility of clipping effect. Okay, so this is the important takeaway related to this last example.